Let's start by assigning bolts within the model. The bolt idealization tool allows us to create beam element representations of bolts to aid in the setup and solve portions of our simulation. Currently, the bolts are being modeled as generic bodies, but assigning them bolt properties will later allow us to report bolt-specific performance results. Additionally, we'll be able to reduce memory allocated for bolts and increase the speed of our simulation by following this modeling approach. We can begin by hiding and excluding all nuts from the simulation. It's recommended to hide nuts, washers, and any other attachment hardware prior to assigning bolts. Select the mount nut compartment in the geometry tree and turn off the options on the left. Now, switch to the Prepare tab and navigate towards the bolts group. Here, you can see we can assign and create idealized bolt geometries as well as display them as beams or 3D elements. Click on the Assign button to begin. Let's start with the bigger front mount bolts. Hover over to one of the bolts and select the suggested highlighted geometry. It is important to note that you are going to be selecting the inner diameters of the hole where the bolt is installed. You will not be selecting the bolt geometry itself. We'll select all similar bolts by clicking on this button in the HUD. We can now choose which bolt we'd like to model, but note that Discovery auto-identifies a bolt that matches the bolt hole selected and prescribes a shank diameter, a head diameter and height, and a variety of material properties that are specifically tied to the grade or class of the bolt. You can filter through different bolt libraries as well. Additionally, if you are ever dealing with bolt holes that are not adjacent to one another, you can click this button that allows us to select coaxial holes that are separated. For our example, the suggested bolts are good, so we'll accept or hit enter. Let's repeat the process for the smaller bolts. Select a set of bolt hole diameters and click on the option in the HUD to include all similar bolts. Note that there are some bolt regions that are not included, which may happen with many cylindrical faces. Therefore, we'll select the remaining areas manually. We can simply click on the remaining areas to add them. Let's now review our selection. You'll notice that the app selection includes the bolt and cylindrical faces. We can remove them by simply holding Ctrl and clicking on the unwanted faces. Then click Accept or hit Enter. It is important to understand how Discovery will use these idealized beam elements. This is best understood if we visualize our new bolt elements as 3D bolts. If not on, click on Display 3D Bolts. Discovery connects these beam elements at the projected head and tail diameter that was defined under the Assignment tool. Connecting these elements at the same diameter as the head of the bolt will give us a more accurate understanding of the true effects of the bolt preload. It is important to note that these elements will be connected at the edges of the holes if transferred to mechanical. We can move forward now that we have the bolt modeled. You will notice that we have 2 bolts left in the model that connect to the front mount links. We'll take an alternate approach for these connections. We can assume that these bolts are not of interest and we just want to capture the joint connection at these locations. So first, let's remove these bolts. Click on each bolt in the geometry tree, then right-click and select Exclude from Simulation. Right-click again and select Hide. Now, let's create the joint connections. To do so, we'll need to access the structural tools. Let's do this through the halo this time. Navigate to the structural tool and select the joint option. From the drop-down list, select Hinged. Now zoom in to one of the links and we can start to create the joint. We'll have to select a primary side, so let's pick the link. And then we have to select the secondary side by clicking here. Let's pick the main mount. Note that it does not matter which side you choose to be primary or secondary. Additionally, you can select a secondary face by holding Alt instead. Now, click Accept or hit Enter, and let's repeat on the other side. Once complete, we'll be able to see the hinge joint connection in the physics tree. A few things have happened in the geometry and physics trees. In the geometry tree, the bolt bodies will have been switched to excluded from simulation, and a bolt component is created. In the physics tree, you'll notice bolt conditions will appear for each bolt type. As previously alluded to, one of the main aspects of modeling bolts in simulation is to understand the impacts of the bolt preloading process. To apply a preload to each of these bolts, we can navigate to the structural tool and select Bolt Preload. We can manually select individual bolts, or we can select entire groups. For this example, let's select all bolts and enter 15,000 newtons for our clamp force. You can also define preload by grip length adjustment or torque. Note that 15,000 newtons will be applied to each bolt, and is not a total summation. Now that we've defined our preload, we can solve. As soon as the simulation begins to solve, turn on scale deformations to easily see results. Discovery automatically creates two load steps where we will apply the bolt preload in step 1 and then other physics boundary conditions in step 2. We'll start to see deformations for the bolt preload. And now we'll see deformations for the other boundary conditions. Now that we've modeled bolts, the next step we'll take is to update the bonded contacts to model more detailed interfaces.